Welcome to The Next Human. My name's Arav, and today I'm joined by Dr. Udit Halder, a postdoctoral research associate at the University of Illinois Urbana-Champaign. Thank you so much for being here today, Doctor.
Thank you so much for inviting me. I'm glad to be here.
Great. So let's get started. The first thing I wanted to talk about is, so what is your story? Like, where did you, so can you kind of walk me through your journey, basically, to get where you are today?
Yeah, so I'm from India. I grew up in a city called Howrah, which is next to in the city called Kolkata, is in eastern part of India. So I did my schooling in Howrah and then did my bachelor's in Kolkata. And then after that, I came to the US, to University of Maryland for my grad school. Basically, I did my doctorate studies at Maryland. And after graduating, then I moved to Illinois, where I'm currently at working as a postdoctoral researcher.
Great. So how did you, get interested in this field of like soft robotics and all this, super cool stuff you're doing?
Yeah, so it's an interesting story. Basically, when I joined Maryland, right? So my doctoral study was in electrical engineering. And as my part of my thesis, I was studying like how barred flocks behave, right? And then I was looking at what would have later helped me transition into soft robotics was some continuum description of bird flocks or any flocking in nature. For example, you have fish, school fish, and a swarm of birds. But if you look at them at an aquarium or even in the sky, so they're very, very fluid, right? So and then they can change their shape very, very naturally, and it's amazing how they do that. And even now, we do not have a good understanding how they work. So as a part of my doctoral thesis, I studied to mathematically model that kind of swarms as a continuum system. So basically lots and lots of birds or lots and lots of fish. So then we can then model them as a whole thing, as a continuum, and then moving in such a way. And they're individual agents on that continuum. They're like, they're interacting with their neighbors in such a way. So the whole group emerges. So that's something called emerging property from a group. So as I was doing my PhD and I was getting close to, graduate, I was looking into how I can, so because I wanted to stay in academia, so I was looking into how I can extend this kind of studies in doing something more along these lines, right? So then this project of CyberOctopus that caught my eye, and I applied for being a postdoc in this project. And then I actually was recruited on that from the very beginning back in 2019. So the idea of this project was to, look at the octopus and then understand how it behaves, how it works, right? So the research in soft robotics, it is not very old subject. It's actually started to get researchers or scientists' attention for about 1 or 2 decades at max. So, so previously, if you look into literature, engineering literature, like in 70s, 80s, people were looking into how arms you can control and how you model arms, but those arms were, rigid arms. So what we call articulated robots, right? So there was a lot of research had been done at that time to characterize, to model that kind of robots. But then as technology improved, people were thinking, okay, so now we have done this, rigid robots, how we can move on to the next thing, which is now you do not have a skeleton, you do not have joints, now you have a continuum soft body. and how you can control that, how you can model that in the first place, right? And then to do anything like this, you need to like look at nature, how nature is doing, how nature has solved these problems. And there's nothing better example than the octopus. The octopus is a soft creature, it has 8 arms. All of those arms are very, very flexible, very soft. But it doesn't have any skeleton, right? But even without a skeleton, the arms can do a lot of impressive things. So people then started to think about how we can capture that and how we can, studying those kind of systems, how we can then build a robot someday that would do something like that, and we can use that in various applications. To name a few, you can use like an arm like that in agricultural applications, where you can, it's a berry picking robot. You can go in unstructured environments and then pick some fruits that would have been otherwise very hard to do with that other kind of robot. So you can automate that process. You can even use this kind of very flexible robots in medical field to do surgeries, right? You can insert these robots in humans, for example, and people are looking into this kind of next generation devices that can do automated and very, very accurate surgeries on humans. And there are many other applications as well of this.
Great. So you guys are saying, like, I understand that like the octopus is, wide range of applications and everything. I'm wondering, I've seen some like videos and stuff of like your guys' simulations. And I'm wondering like where do you see yourselves in the process right now? Like how far along do you think you guys are from, getting that like, hand basically operational?
So basically, when we started to look at octopus back in 2019 and trying to model, for example, my part was to model the arms, but the project is even larger. We wanted to look at the whole of the octopus and then try to get a computation and analog of an octopus. So working octopus inside of a computer, it looks easy, but as we have learned over the years, it's a tremendously difficult problem. So even after a few years of study, we do not fully understand, well, we're nowhere near close understanding how complicated that system is, so it's gonna be so in the process, right? So I believe what we're doing now is because we have studied a little bit and we have some knowledge about it. So we see ourselves working on this field for many years to come, and lots of unanswered questions have popped up, which we would like to investigate further.
Great. And so this is kind of like a question about the octopus in general, but like why the octopus basically, and why, like, what does mimicking the octopus's like unique structure like enable? And
so as I already touched upon it a little bit, is that when you try to understand something, so the inspiration comes from the vision that at some point of time you want to get a very flexible robot, a very soft robot. But to do that, first we need to understand its working principles. And what better organism is out there to study soft-bodied animal than octopus, right? It's insanely complicated, and from a computation point of view, when you think about the octopus, is right. So sure, it has a soft body, soft arms. It can comply. So the arms can comply with the environment. So it can push its arm through some, tiny holes, and then it can even push its whole body through a tiny hole. It's amazing. But also, from a scientific point of view, it has a mind that is not like anything else. So if you think about other animals, humans even, so we have a brain, right? So all the computation, whatever we do, so that all goes on inside our brain. So all our neurons are inside our brain, computation neurons. So then, so this is called a central nervous system, right? So basically all the computation is centralized. But octopus is not like that. So it has a brain, but you would be amazed if you didn't know, most of its neurons, they are distributed throughout its body. So
wow.
it's actually, so it has like pockets of neurons situated on its arm. So it's actually called a distributed brains and a distributed body. So it has all these computational units located along these arms. And then biologists have studied this for several years, but no serious study has been done, like from modeling and mathematical point of view, to understand, what is the computation that the octopus is doing, because we are pretty certain that biologists have shown it time and time again that it doesn't, much of its computation for manipulation, whatever it does, much of it's done peripherally at the arms. So each arm has their own brain, actually not single brain, like multiple brains distributed in its arm. So what is that it's computing, and how that enables the animal to do complex tasks. So this is some sort of a learning mechanism that we do not understand. We don't know how this works. So the idea was to understand this kind of system. It's very different from the other kind of nervous system that you see in other animals, humans included.
So are you guys also working with a team of like marine biologists or like biomechanical engineers?
Yes. So this CyberOctopus project is huge. So it includes biologists, neuroscientists. So basically what they do is they catch octopuses. So actually in our campus, we also have, live octopuses in the aquariums. And then, so they do several kinds of experiments, right? So they do behavioral experiments for the octopus, like behaviorally doing, and try to understand what is most common behavior, and then how we can understand those. And then second is they dissect, right? So dissect the arms, and then take recordings from the arms, and then so this is the second kind of experiments that the scientists are doing. And then there's another part of this project which involves developing next generation sensors to record from these arms as the octopus is moving in the tank. The idea is to implant these sensors on the arms or on the brain to record from it as it's doing something. So that's never been done before. It's kind of like it is next generation idea. And then third is us, which is we want to model this thing from a mathematical point of view, and then try to understand what are the control strategies for the octopuses. And then we have to collaborate with, because these things are so complicated, we cannot just do it in pen and paper. So we need computers to do our simulations, because these things are, represented by very complicated mathematical equations. So we need powerful computers to simulate those equations. And that's where the other part of the team comes in, who does these high fidelity simulations in computers. So we then use those simulators to see, like, test our control algorithms, right? So we want to understand how the octopus is controlling things and how it moves, how it manipulates. So all this is coming together with the collaboration with other parts of the project. And then finally, there are computer scientists who are involved, who try to use learning algorithms to understand how learning is happening in octopuses. So that's another part of the project as well.
Wow. That's really massive project. This is a little bit of like a fun question, but have you seen Spider-Man?
I
Uh,
have, yes,
uh,
yes. So
and
basically, yeah, we just went to see it last week, and it blew my mind.
yeah, and so yeah, all this like Octopus talk is reminding me of the Dr.
Doctor.
Ock, yeah,
Yes,
Dr. Octavius, and now
yeah.
I'm just wondering if part of like the end goal could be kind of like recreating like a Doc Ock suit in real life, and
Well,
that
maybe.
that'd be pretty cool. But
But not to use it for evil
oh yes, of
purposes.
course, of course. um, but yeah, so I think that's really amazing stuff. So another thing I was kind of curious about was like the whole concept of biomimicry and
Mhm.
how so the kind of I guess the question I'm trying to ask is, were you guys choosing to imitate nature because of just how efficient it kind of solved this problem of like flexible robots?
Yeah. So yeah, so basically, um, the idea here is to, if we understand octopuses, then we don't need to. So because these things are so complicated, right? So in technical terms, these are called infinite dimensional systems, and it has infinite degrees of freedom, right?
Mm.
So if we were to try to fabricate something like that, or even try to come up with control for that complicated system, we would be very much in middle of nowhere, and we'd have to like go try many things and see what works, what doesn't.
Mm.
And that would be a messy process, and you may not get anywhere. So on the other hand, if you look at nature, then you'd see that these problems have been solved uh, not by somebody, but by evolution, right? So nature has been trying to solve this problem over millennia, right? And then something did work, something didn't, and then what worked, the nature has selected that, and then that evolved over the years. And then so now we have this end product, and then we're trying to go back in time, like how it evolved,
Wow.
and try to understand the working principle. So if we understand that, then this problem immediately becomes way simpler, because we are seeing like an optimized. So we need to be a little bit careful though, because it's optimized, but optimized for its like use in that environment. So the theory of evolution says that it's not the fittest, survival of the fittest, but it's fit enough, right? So it just have to survive that environment. So that's the idea. So 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 that's why it's good to study not only one organism, but other organisms. So what are the other ways nature has solved this problem to do it? So if we understand these principles, these various mechanisms that is already out there, the solutions are out there. We're just it's kind of like cheat sheet. So we're looking at the right. So we're looking at the solutions that's out there, and then using that, and then try to understand how do we build our own robots, and then what are the controls that we can put in our robot, which would be efficient and energy conserving, for example.
So you said you guys are also looking at like other mechanisms and other things. So other than the octopus, were there any other like organisms you guys were looking at and kind of trying to
Not
understand?
currently, not currently, but But other groups, other researchers have also been looking into other animals, like in the squid, like in the molluscan category, there's also squids. People have been looking into that. Also, the starfish, so their crawling principle. So these are marine animals. In land-based animals, so people have been looking into, the caterpillars, how the caterpillar moves. Also, yeah, so there are many animals that we could look into, but to remind ourselves is that each animal, it's a world of its own, so it takes several years to understand. So we just started to look into octopus, and we are like, okay, this thing is hard. Needs serious work, so it's not easy.
So you mentioned kind of like two phases. So one like understanding the mechanics and how exactly the arm operates. And then after you guys, fully lock it down and everything, understand how the arm works, then you can shift to replication and like testing out these arms. And so from, I think what you were saying is that you guys are still still in the like understanding phase. And do you guys have sort of like a timeline or something that you guys are expecting, or do you think it's progress is happening, but it's hard to measure?
So I would say, so academic research has kind of like various ways, right, to work on these problems. One is that purely just studying from a scientific point of view these animals, right, octopuses, and from many different perspectives, from biologist perspective, from engineer's perspective, so that could take a lifetime. If you just study one organism, that could take a lifetime. So that is a work that can build up on its own. But then there's also the other side, which is the robotic side. So roboticists, what they try to do, they try to build something, build a robot, and then try to control that. So there's these two parallel lines, and then they don't have to interfere with each other, but what they can do, they can complement each other. Mainly the robotic side can get a lot of intuition from the biology or the science of these organisms to then implement in their robots and make the robots better. So I guess there's these two avenues of research which are actually in progress, and it's going to be in progress in the coming years.
Right. And sorry, you mentioned earlier, but I was also curious just to hear more about the applications of the octopus arm and stuff, and kind of what we could expect to see octopus arms doing in the future.
Yeah, so as I mentioned, two applications before. Again, for example, you could use it in automated agriculture, where a soft arm could go in a field, and then so it could be attached to a mobile robot. The robot goes near a tree, and then the arm could go and then can get the fruits, for example, berries, strawberries, or what have you, more efficiently, and then fetch that to the robot. So that's one application. The other is again in surgery. You can have these robots doing surgery for you. They could be more precise and less invasive, so you don't have to cut open a body, and insert it into arteries or something like that, and then they can follow the route and go to the source of the problem and solve it there. So there are many researchers who work in the medical robotics field who have been trying to develop this kind of robots. The other application would be like so because these robots can work in unstructured environments, so they can comply with the environment, so they can be used in search and rescue missions where you have lots of rubbles, but where a traditional robot would get stuck because it cannot move, but the soft robot can find path and then follow the rubble and then find an opening to get through and then do what it needs to do there.
Great.
So these are among a few, few applications.
Wow. Great. And yeah, so I mean, that was great. Thank you. And I think, thank you for this interview. And I'll just ask one final question to, wrap this up. And it's basically, so, with like technology and innovation growing at such a fast rate, what is like one piece of advice you'd give to, young learners, like high schoolers like myself that are just starting on, their professional lives and, and with like everything going on in the world.
So it is easy to get overwhelmed by what's happening all around you, and the technological field is advancing at ever exponential rate, right? It's mind-boggling. So even the scientific field, the technological field, they're trying to catch up, like what's been happening very recently. So, but again, so it's kind of cliched advice, but what I've learned over the years is that there's no shortcut to success. So if you're passionate about something, do not give it up, right? So you have to do the hard work, you have to do your homework, to be honest with yourself and pursue that passion over the years, and success will follow. So you cannot make it quick. So.
All right. Thank you. Thank you for that advice. And thank you for, agreeing to be here today. And yeah, that's it. So
thank you very much.
Thank you.